Okay, let's get started. This week, as I mentioned, we have no labs. Okay, so tomorrow and Friday, no need to show up. Okay. So, anyways, before we begin, do you have any questions? Okay. In this class, 18 students are enrolled. I think some students are missing. Okay. I mean, as I mentioned, if you guys are gonna kind of miss classes, just kind of send me an email, okay? That's gonna be no problem, okay? But just kind of a extended period of time, like absence is actually, no good. So, yeah, I'll sometimes check attendance, but if you happen to miss class, just let me know, okay? Send me an email. Okay. This is not about approval, okay? Just kind of notifying me that you're gonna miss, all right? Okay. So then we are gonna actually continue on this scaling law, okay? So in this topic, what we are trying to see is, as we scale up and scale down, what kind of factors become dominant, okay? So for example, as we discussed yesterday, as we just scale up and down, and it turns out that actually the supporting leg has to be scaled differently, right? So for example here, like as we kind of just scale all the way up, like including leg and body, it turns out that leg cannot really support the body weight, right? So in order to withstand the same pressure, what you have to do is that you have to actually scale a little bit, larger kind of a fraction, right, to support the same pressure, okay? So that is essentially kind of what we found out yesterday. And then let us now talk about the surface tension, okay? So surface tension is the surface force existing on liquid, okay? So basically surface tension is basically, like a liquid trying to minimize the surface area, okay? So for that, like that is why we see, basically bubbles formed by soapy water. Okay, it kind of tries to minimize the surface area, and it turns out that the sphere, okay, or sphere shell turns out to be the minimizing surface area. Okay, so for that one, basically like if we kind of look into kind of force balance of this kind of spherical kind of liquid shell. The force due to surface tension kind of acts on the surface or perimeter here, and then this force is balanced with force due to basically inside air pressure. Okay, and this surface tension force can be obtained by this surface tension. Okay, this is actually the property of the liquid interface. Okay, so for example, if you're dealing with, commonly, it's a liquid air, right? And then that liquid air interface property basically kind of defines the surface tension. But obviously, if you are dealing with air or different air, actually, let's say, like kind of like a different environment, such as nitrogen or argon, and then if you are dealing with the same liquid, let's say water, okay, water air interface surface tension is going to be different from surface tension of water like nitrogen. Okay, so in the sense this is a kind of interfacial property. Okay, and then you need to multiply by this L. Okay, this is essentially kind of if you look at this spherical shell, that is essentially perimeter of this circle. Okay. And then now let us look into this surface tension force on a floating plate. Okay, so in this case, this one is a square shape, okay, or rectangular, more precisely here. This is a D, length is D, and then along this horizontal line, length is L. Okay, so then this object has the weight, right? This weight is a downward force, and then surface tension force is upward. Okay, I mean, like I'm not going to get into details, but like the way it works is that this surface tension is trying to minimize the surface area, right? It's kind of, you can think of this as kind of a stretching, kind of thin plate. Okay, you can think of this kind of the layer or interface of liquid and vapor, and you can think of that as kind of stretching plate. Okay, So then, weight is kind of pushing down, but this one is kind of trying to stretch, right? So what that means is that there will be some curvature, right, at the end, and then surface tension acts tangentially at the, kind of this tangentially on this surface. Okay, so that is why it's basically acting upward. So then, obviously, if surface tension force is larger than weight, it's gonna float. But if the weight is larger than surface tension, it's gonna sink, right? So that is essentially kind of what we are gonna look into. So surface tension force is obtained by, again, surface tension times this perimeter. Okay, so this perimeter is essentially, this perimeter. And then the weight we can easily obtain by mass of this object times gravity, acceleration, okay? So with that, I'm gonna just kind of make a little modification. I'm gonna change this mg with this tau times a, okay? So a is the cross-sectional area, and then this tau is the weight per unit area, okay? So what that means is that, weight per unit area times area, that is weight, right? Weight is essentially force here. So, with this modification, we are gonna compare these two downward and upward forces, okay? So basically this is just kind of the same as the previous slide. So what we are gonna do here is that we are gonna scale up and down with just perimeter change, okay? So basically here, we are gonna maintain the thickness, okay? We are gonna fix the thickness, but we are gonna basically scale up and down the perimeter, okay? So if we do that, we are gonna actually define this beta, that is essentially ratio of downward force to upward force, okay? So downward force, obviously weight, and then upward force is a surface tension, right? So, so with that, like weight we already obtained, that is tau times a, that is a weight per unit area times cross-sectional area. And surface tension is simply surface tension times perimeter, right? And then with that, area is essentially L square, right? The length square. And then perimeter is just L. And then we just kind of cancel that out. And then we have only L here, right? So that is essentially, this how it scales with the length scale, okay? So with that, now we can kind of plot this beta as a function of L, right? So what that means is that there will be the equilibrium position, that is essentially when this delta and gamma, or as you increase or decrease by L, okay? So you will see there will be some point where this beta is less than 1, okay? And then that is essentially this regime. And then as we scale up, right, L, now beta is gonna be above 1, right? But when beta is 1, what does that mean? That means weight or downward force and upward force are exactly balanced, right? So if beta is less than 1, what does it mean? Basically upward force, is larger than downward force, right? Are you guys following here? Yeah. So what that means is that obviously body floats, and if a beta is larger than 1, basically downward force is larger than upward force. So what that means is the body sinks, right? I mean, it's just kind of a simple expression here. So this is essentially kind of what we see, in our life here. The common example, water strider and floating paper clip. If you think about this water strider, it's actually kind of small insect, right? And then because it is small, for example here, the L is kind of going smaller and smaller. So it turns out, that is essentially within this regime, right? Beta being lower than 1. Okay, that is why body floats. And another one is, paper clip. Okay, so if you kind of drop the paper clip gently on the water surface, it floats. Okay, but with this scaling law, you can kind of tell. If you make larger paper clip, like with the same wire thickness, it's gonna basically following this scaling law. Now L is gonna increase, right? And then it will eventually get into this regime, and the paper clip is gonna sink, Okay, so this is essentially, like what happens with the scaling law, right? I mean, we didn't even get into quantum mechanics, but as you scale up and scale down, like a different effect kind of arise, right? So as you scale down, it can float, but as you just simply scale up, well, it doesn't necessarily mean that it's going to float, okay? Because there is actually kind of competition between two effects here, right? Basically, downward force and upward force. This one is closely tied to scaling. Does it make sense? Okay, so like now, like for example, like this one is a kind of floating, and then I'm gonna make a kind of a larger paper clip. Okay, it doesn't necessarily mean that it's gonna float. Okay, so in the sense, when you are kind of approaching with the engineering problems, this is scaling up and down is sometimes not really kind of a straightforward solution. Okay, you have to kind of carefully analyze, like what effects will dominate, like as you scale up or smaller. Okay. So and then now we can look into this fluid mechanics. Okay, I mean we are going to go over several examples, in this topic. Okay. So here, like basically we have conduit here, okay, and then there will be pressure drop as a flow, liquid flows through this conduit, and the radius of this, smaller, like a hole here is A, and then here we are essentially kind of maintaining the flow, okay, like flow in and flow out Q, and then we can actually obtain this volumetric flow Q from this Hagen-Poisson equation. Okay, so that one is essentially given by this equation here. Pi a, this is a radius to the power of 4, and delta p, that is a pressure drop over 8 times, viscosity and the length here. Okay, so basically, like by looking at this, you can immediately tell, like what is the length scale here, right? So basically, this a to the power of 4, and L is there, and then delta P. So it turns out that this Q is proportional to the power, proportional to A to the power of 4. Okay, so basically, like if we just focus on just a diameter or radius, it has this relationship. Okay, so what does it mean? If we reduce this conduit radius by 10, okay, the reduction of 10, what that means is that the volumetric flow is reduced by 10,000, right? Because it has kind of a, this, like fourth power, okay? So that is a kind of a one observation we can make, and also let us look at this pressure drop, okay? So, like we are using the same equation here, and then if we just express in terms of pressure drop delta P, now this is what you get, okay? So in this case, if you look at it, like there is delta P, and then L is there, and then I'm going to move to the left-hand side. So what that means is that now we are looking at pressure drop per unit length, right? Because delta P of L, and the L is the length. So this is a pressure drop per unit length is proportional to A to the power of negative 4. Okay, so what that means is that as we reduce conduit radius by 10 times, okay, so what that means is that now the pressure drop increased by 10,000 times. Okay, so what does it mean? Basically, as we make smaller pipe, the pressure drop significantly increase. So that means, in order to drive the flow, you need very strong pump, right? And then it's actually very hard, like if you are dealing with a very small one, okay? So, for example, if you probably heard about like a nanofluidics, stuff like that, okay? And then if you are dealing with kind of pipe with like a micron size or, like even nano size, imagine how much pressure drop is going to happen in that pipe, okay? So for those applications, you cannot really use the pump because, you need a very strong pump to drive flow in a tiny channel, okay? So people typically don't use the pump, and what they actually typically use is basically using different mechanisms, like capillary reaction, okay? So like with a kind of a use of a surface kind of force, they can drive the flow. Okay. So again, here, like we are not even getting into like a very small scale, like a just kind of in micrometer scale, because of this limitation, like the pumps that you typically use for bulk scale, they cannot even be used. Okay, you have to use different mechanisms. Okay, because of this simple like scaling law. Okay. So, and then let us now look into some examples of solid mechanics. Okay, this is a simple cantilever beam. Okay, with the length of L, and now we are applying the force at the end of the beam. Okay, so then as we apply the force at the end of the beam, there will be some deflection developed, right? And also this cantilever beam is just kind of rectangular shape. Okay, the width of that is a B, and the height of that is H. Okay. So then, using this simple Hooke's law, okay, F equals K, basically spring constant or stiffness times delta deflection, right? And then you can obtain this K, okay? So I assume you have taken solid mechanics already, right? So then you probably derived how you can obtain this stiffness, okay? Or I mean, now you have taken it. So now, if you want to get this stiffness, what you do is look at the appendix of the solid mechanics textbook, right? Then it has various examples, and then it has like all the expression for spring constant, like bending moment, etc. Right? So with that, you can obtain this K. It turns out it is 3 times Young's modulus and the second moment over area over L cube, right? So here, the I for this simple rectangular shape is essentially 1 over 12 BH cube, right? So that is essentially like how you can obtain this delta, and then you basically kind of plug it in, and you can obtain this K. Okay. So with this cantilever beam, we are going to consider these 2 cases. Okay. So obviously, we are not going to change the material. So what that means is that we are dealing with the same material property. Okay. So for example, Young's modulus does not change if you don't change the material, right? And also, we are not talking about nanomaterials. So what that means is as we scale up and down, we are still in bulk scale. So material property does not change. Does that make sense? But if we get into nanomaterials, material property is going to change. So that one is going to be a little bit tricky. But in this discussion, like we are still talking about the bulk scale material. So as you scale up and down, we are still maintaining material property. Okay, and then we are going to scale in all dimensions. Okay, so in the sense, basically length, like by factor of 2. B by a factor of 2, H by a factor of 2, like that. Okay. So then, if you look at this K, it has a B and the H cube, L cube, right? So basically, this is a length to the power of 4th, and then here length to the power of 3rd. So we essentially cancel out, and then we have only L left. Okay. So what that means is that as we scale up, right, the stiffness increases, or spring constant increases. Okay, so basically, by looking at this, we can make a conclusion that larger beams are stiffer. Okay, and then the second case. Okay, so we are essentially again maintaining the same material property, Young's modulus same, and then here we are gonna fix the H. Okay, so for example, here the height is fixed, but we are gonna scale up and down with this B and L. Okay, so if you do that, basically H is fixed, right? This one is essentially constant value, but B scales up and down, and this L scales up and down, right? So B is a length, and then here L cube. If we cancel, basically we have K is proportional to the inverse of L to the power of 2, right? So what that means is that now, if you increase, right, if you scale up, now K goes smaller, or if you kind of scale down, K goes higher, right? I mean, that is essentially kind of what we obtain from this scaling law. Okay. And then, like this is just another example. Okay, so what if no external force, instead we are dealing with just cantilever's own weight. Okay, so previously we applied the external force at the end, but now no external force, but we are dealing with just kind of body weight. Okay, the beam's weight itself. So then again, in this case, like we are introducing another kind of a new parameter here, the small w, that is essentially, the whole weight over the length of the beam. Okay, so what that means is that this small w represents weight per unit length. And then for this case, you can obtain delta. It turns out that is a WL to the power of 4 over 8 times Young's modulus times the area moment. Okay, and again, this I area moment is the same as 1 over 12 BHQ. Okay, so then we obtain K, because we already know what delta is. You just kind of substitute it here, and then that is essentially kind of what we obtain. Okay, so with that, we are going to again consider two same cases. Okay, so again here, we are scaling in all dimensions, even B, H, L, all scale up and down. So we get the same expression, okay? So K is proportional to L, and it's the second case. We are essentially scaling up and down with L and B, but we fix the height, okay? So in this case, again, we get the same expression as K is proportional to the inverse of L to the power 2, okay? So smaller beams are stiffer, and the first case, large beams are stiffer. Okay, so with this one, like you can kind of easily see. Okay, so for example, like think about this paper as the cantilever, right? So here, we have a like let's say L, and then this is a H, and then this is a B, right? And then with this one, like it's kind of like a bending like that. Okay, stiffness is like let's say this much, but I'm gonna just scale down, but we are fixing H. Okay, so what I can do is I can just easily kind of cut it, right? Like just like that. So in this case, H is fixed, but B is reduced by a factor of whatever, right? And then also this B is L is reduced and the B is reduced, but H is maintained, right? But if you look at it, it doesn't bend as much, right? Why? Because as we scale down, this beam gets stiffer, right? So that is essentially kind of how you can see, like just with the kind of scaling, it's not just about miniaturization, okay? So different effect. In this case, basically stiffness increases as we scale down. Okay. So, and then we are gonna again continue on this, cantilever beam due to body weight itself. Okay. So in this case, we are gonna consider bending moment. Okay. For this bending moment, we can obtain this maximum bending moment that is essentially 1/2 WL square, right? Because like if you look at it, the body weight, this W, and then do you remember this is small w? Small w is the weight per unit length, right? So WL is essentially acting at the kind of the center, right? And then you can easily obtain this bending moment. So then this small w is the weight per unit length. If you express that, that is essentially density times BH, right? BH, and then because it's a kind of per unit length, we don't multiply by L, and L is actually turns out is here. Okay. So from this bending moment, we can also obtain this bending stress. Okay, bending stress can be obtained by this expression. Okay. So then maximum bending stress is essentially like you substitute this into here, and then Y plug it in. And then I, we already know for this rectangular beam, and the maximum bending stress is essentially 3 times density times gravity acceleration L to the power of 2 over H. Okay, so then Now we are gonna kind of apply the scaling law. Okay, so which one has a length scale? This one, L square and H, right? So then if we cancel out, this maximum bending stress is proportional to just length scale, right? As you scale up, maximum stress is going to linearly increase, okay? So what that means is that, like we kind of express here, right, the linear relationship for the maximum bending stress. But, like we already also learned that, material can fail when it exceeds ultimate stress, right? Basically, this is a material property. So what that means is that as you scale up, there will be a point given by ultimate stress, right? So and then let's say this is essentially kind of ultimate stress, right, given for this material type. Okay, so what that means is that, as you scale up, if you are here, you are fine because this maximum bending stress is still lower than ultimate stress, right? But as you scale up, there will be a point where it hits ultimate stress, right? And then if you kind of scale up even more, what happens is now ultimate stress is lower than the maximum bending stress, so that is essentially, it's gonna fail, right? So basically, like with that, you can kind of also understand by this one. Okay, so for example, here, let's consider this case number 1. Okay, as we scale up, what happens to stiffness? Stiffness increases, but like you want to make a very stiff beam. If you scale up, eventually what's going to happen? It's going to get stiffer, but you are going to hit probably this point, right? So and then even though it's a very stiff, eventually because of this, ultimate stress, this beam can fail, right? So, what does it mean? You cannot really make super stiff beam by just scaling up, okay? Because you have to consider this ultimate stress as well, okay? So in the sense, like when you're kind of designing the material, like scaling up and down, you have to consider various components, okay? So, for example, if this one is like a way small, like if you are dealing with a kind of a beam with a kind of within this range, then like as you scale up, you really don't have to worry about ultimate stress, right? And then but at some point, if you are kind of scaling up like substantially, if you don't consider, let's say, ultimate stress, what's going to happen is, like you expect, oh yeah, this is going to be very stiff, it's going to work, right? But when you kind of do experiment, you will realize, oh, it just breaks by itself, right? So in this sense, I mean, this is a kind of a common mistake most engineers make, right? I mean, we kind of overlook certain kind of parameter, and it turns out it is dominant factor. Okay, and then that happens as you scale up and down. Okay, this is actually very commonly observed problems. Okay, so in the sense, when you kind of scale up and down, keep in mind, okay, like you might miss something. Okay. So another kind of example is buckling here. Okay. So buckling, I mean, there are various cases, pinned, or free fixed, fixed, and pinned, fixed. But in this particular example, let us just consider the simplest case. Okay, free fixed. Okay. So in this case, we are applying force at the end, okay, and then this one at the other end is essentially kind of fixed, okay. So for this example, you can obtain this buckling force, okay, like at which point buckling is going to happen, okay, buckling failure. So that is given by this expression. So again, if you look at it, this is Young's modulus and I here, and then h squared, okay. So I, as you know, for this rectangular shape, it has BH cube, right, relationship. So it then says L to the power of 4, and then here h squared L to the power of 2, right? So you cancel them out, and then this buckling failure force is proportional to L squared, okay? So then, imagine the object is kind of attached at the top of the column, and then that weight is essentially considered as a force, right? Downward force. Okay, so then that weight or this downward force is due to the mass, right? And then that mass is related to density times volume, and then volume is essentially L cubed, right? So what that means is that we can kind of see here, okay? So this is L cubed, so initially it's kind of slowly increasing, but later on it's going to rapidly increase, right? And then there will be cross point here. So what does it mean here? So F buckling is still higher than F mass, so at smaller range here, we are safe, but after this point, this F mass is larger than the failure force, so this is essentially where buckling is going to happen, right? So then now we kind of compare this buckling failure versus compression failure, okay? So in this case, I mean, this is just kind of a representative example, okay? So here, this is the kind of the object attached to the beam, okay? And then this is the beam, and then we are just kind of arbitrarily setting this height of the column, this h, as x. This is essentially kind of scaling fraction, okay? X is scaling fraction, and d is the diameter of the sphere, okay, object here, okay? So with this setting, we are going to kind of investigate how the scaling kind of influence buckling failure and compression failure, okay? So for this one, let us kind of look into that. And buckling failure, as we saw, that is essentially this expression, and I'm just kind of writing it down here. And then as I kind of set by example, this height is essentially x, this fraction times diameter, okay? And then now I'm replacing this h with x times d, okay? And then, like I'm including this I as well, that is essentially pi over 64 d to the power of 4, okay, for circular rod. And then this is, the mass downward force, okay, weight, okay, weight of the sphere, okay, this is essentially what you get. And then if you are equating these two, basically, you get expression for this d, okay, the small d is essentially the diameter of this rod, okay? And then this is what we get, and then here, look into the ratio, okay? So in this case, this d length scale to the power of 5, and then this one has to the power of 4, okay? So you kind of move it to the right-hand side, and then, this dB, or rod due to buckling failure, is proportional to large d to the power of 5 over 4, okay? So large d, again, just reminding you, that is the diameter of the sphere, okay? And then what is the criteria to prevent compression failure? Okay, so in this case, we are going to essentially consider ultimate stress here, okay, ultimate stress, and then we are basically evaluating this weight due to weight from the sphere, and then area is the cross-sectional area of the rod supporting, okay? So once you do that, you basically obtain that, and then now you are evaluating basically the rod diameter for ultimate stress failure, okay? So then now we have this d to the power of a third, and then here, the small d square, and then that is essentially large d to the power of 3 over 2, okay? So then with that, now we can kind of plot, okay, here, the failure due to ultimate stress and failure due to buckling, okay? So then if you look at it, this dc, okay, this is 3 over 2 is larger than 5 over 4, right? So in this case, basically dc is going to slowly increase, but later on it's going to basically kick off, and then it's going to be larger than dB, right? So what does it mean here? So since this dB is larger than dc, this is essentially the domain where buckling failure is going to happen first, okay? But if we deal with larger scale object, the failure is driven by compression, okay? Like compression of failure, okay? So in the sense, just by looking at this one, you can kind of ask this question: which mechanism governs a small, like microscale supporting device? Like if we are dealing with a small scale object, most failures are due to buckling. Okay, so actually you probably saw this observation as well. Like if you're dealing with a very small scale object, like let's say hair, okay, like our human hair, okay, it's kind of small scale object, and if you kind of give the force at the top, it's kind of hard to see failing due to breakage. Okay, it's often, you often see buckling. Okay, so in the sense, like if you're dealing with a kind of very small scale object, people often ignore compression failure. They always focus on kind of buckling because, like as you see, this kind of a tendency, because the buckling failure is going to happen first. Okay, so again, in this case, you can kind of see that, like depending on which scale you are looking at, like the focus of failure analysis is going to be very different, right? If you are dealing with, let's say, structural kind of a material, like a bridge or building, nobody cares about buckling, right? Because it will be driven by compression failure, okay? But if you are dealing with like a micro scale objects, they don't even look at the, compression failure. They look at just buckling, okay? So again, I mean, we are still using classical mechanics, but depending on like which range you are looking at in terms of scales, right? I mean, different effect, right? Like in this case, buckling or compression plays a different role, right? Okay, so up to this point, do you have any questions here? Okay. And then now we are going to look at this dynamics, okay? So, I mean, obviously, force is required to change the motion of an object. And, when designing a dynamic system, we often interested in, require force to move a part and how fast the desired move can be achieved and how easily it can be stopped, okay? So here we are going to just kind of apply the Scaling law for various dynamic property, okay? I mean, it's a very straightforward, but just kind of, recap. Displacement, obviously just meter, and velocity, meter per second. That is, like a length per time, right? And acceleration, meter per second square, and then there's an L over T square. And mass is proportional to volume, so that's why L cubed. And force is mass times acceleration, so you just kind of multiply this mass times acceleration. And work is a force times D, right? And then force, we have that, and then D, you just multiply that, right? So then we have L to the power of 5 and over T to the power of -2. And the mass moment of inertia is simply m times r squared, okay? And then that is essentially, like L to the power of 5, right? Because m is essentially the proportional to volume, okay? So then, like if you're just particularly looking at just mass moment of inertia, right? So, like in microsystems, due to extremely small mass moment of inertia, because, as you scale down, the mass moment of inertia decreases very rapidly, right? L to the power of 5, okay? So what that means is that for a small object, mass moment of inertia is very small, so it can instantly start and it can instantly stop, okay? That is actually kind of advantage why we sometimes want to use a micro scale kind of dynamic system, okay? Because, like very easily started and then very easily stopped right away. So in the case, like this is a kind of one example of, natural frequency or resonant frequency. So we are again considering this like a beam, okay? But in this case, imagine this is a very small beam. Okay, so then angular natural frequency or resonant frequency, as you probably remember, that is given by square root k over m, right? K is a spring constant, and mass is the, like the mass is, the mass of the object. Okay. So this k is essentially, like f over delta. This is what we obtained before, and then we just substitute this k with this beam expression. Okay, So then mass, we already know that is A times L, that is volume, and times density. And then if you just rearrange, this is what we get. And then this I is essentially L to the power of 4, right? And then L to the power of 4 cancel out, and then we have area in the denominator, and then we have a square root here, right? So then if we bring that out, now natural frequency is proportional to the inverse of L, right? So then again, the size of the beam changes, okay, keeping the dimensional proportion same, okay? So what that means is that as we scale down, natural frequency increases linearly, right? You see that? So what I mean, as device miniaturizes, angular natural frequency increases, and typical frequency of microsystems and micro devices can be quite large. Okay, like look at this range, megahertz and gigahertz. Okay, so for example, this one, I'm not sure if you can kind of see. This is actually kind of a micro beam. Look at this scale bulb. This is a 10 micrometer, 2 micrometer, 500 nanometer, and 200 nanometer. Okay, and then if you look at the natural frequency here, this is essentially around 50K, okay, 50,000 hertz, and this is 1.6 megahertz. This is about a little bit less than 8 megahertz, and in this case 127 megahertz. Okay, so this one, as you scale down, you can kind of clearly see the natural frequency increase, right? And because of this large frequency, actually people use this simple cantilever as mass sensing and molecular detection. Okay, because imagine, like now natural frequency is very large. We even with a very small change of mass, right? Let's say people actually kind of coat this beam with a specific kind of ligands, and then where some kind of bio object can be attached. Okay, and even with a very small mass change, even a 1 milligram or 1 microgram, with the mass change, this natural frequency can be shifted, right? Because there is a mass here, right? So as you change this mass, this natural frequency is going to be shifted, and it can easily detect those mass changes. Okay, so this one is actually quite common technology available here, and then that is essentially using this dynamic system. Okay, so I mean, another example of a natural frequency is the washing machine. Okay, sometimes when you run a washing machine, at certain kind of a point, when you are kind of putting big blankets, whatever, the washing machine vibrates crazy, right? It kind of bounce around, right? And that is essentially, it was so close to the natural frequency, right? Because as you drive the system near the natural frequency, it kind of the action, motion is essentially exaggerated, right? So the way you kind of prevent that kind of thing is essentially by putting, let's say, detergent, like a bottle, okay? I mean, that one is not that heavy, but you kind of put it on top of the washing machine, okay? So then what it actually does is, because you are changing the mass of the washing machine, what you do is essentially changing the natural frequency. So by just changing that, think about it here, at this natural frequency, this motion is so crazy, right? But if you kind of go a little bit away, what happens? Nothing, right? No response. So in this sense, but obviously, unlike washing machine, in this case, we are essentially using this, the motion due to natural frequency, the motion near the natural frequency. That's essentially how we detect, the mass change. Okay. So anyways, at this point again, as you scale up and down, this natural frequency changes, and that one can be utilized for detecting mass changes and chemical reaction, etc. So another example is the free fall. Okay, so if we drop insects, mice and horse, high up in the building, we know what's going to happen, right? And then that is essentially related to, again, kind of the scale law, okay? So for example, like if we drop object from high altitude, and then, if we drop it, initially the velocity kind of increases with a kind of, acceleration, right? And then it'll eventually reach terminal velocity, right? And then that is due to drag force, okay? So obviously, if we don't have drag force, the acceleration, this kind of slope is constant, right? And then, it'll kind of keep increasing the velocity. But, because we have air and then we face the drag force, and then that one is related to this 1/2 rho CdA times, this velocity square. And, this rho CD half, 1/2, I'm just kind of lumping that into this just one constant C, okay? Because this is not really important. This is just constant, okay? So then if we equate them, this velocity is essentially square root mg over ca, okay? This is c again is just kind of lumped constantly, okay? So there we are gonna see on the length scale, the mass, okay? Again, this is the proportional to volume, L to the L cube, and area, L to the power of 2L squared, and then you can cancel that out, only L left, but we have a square root, right? That is essentially L to the power of 1/2, okay? So what that means is that, as basically the terminal velocity is proportional to L to the power of 1/2, right? So as you scale down, what does it mean? Terminal velocity decreases, right? So the gravity does not really impact much on small insects. Okay, that is why, when insects fall from high, they don't get hurt. But for large objects, because of a high terminal velocity, the damage is greater. Okay. So implication at small scale, like a very small particles like a dust and pollen have a very small terminal velocity. Okay, and then sometimes it remains suspended in air. Okay. So again, depending on this kind of size of an object or scaling, even terminal velocity is significantly affected. Okay. Okay, so I have some more examples of electromagnetic parameters and thermal properties, but for this one we can cover next week. But yeah, we can end here. But before I finish, do you have any questions? Okay, if not, we are good.